Alright, so probably one of the easiest and therefore most difficult topics in math is this idea of probability. And because it's not that much to it, students get very confused about how it all works. So I'm going to try to break it down into a simple process. And I usually start my class by taking a coin out of my pocket and start flipping it and recording heads and tails. Well, I can't do that here, but I went to a website that actually has a coin toss simulator. And you could do a Google search for this and mess around with it a bit. And I allowed the program to flip a coin 50 times. And what happened was that it ended up being 28 heads and 22 tails. So this is what's called an experiment. I went out and I flipped a coin 50 times, and my experiment was literally just flipping the coin, and what I recorded was what happened. So what happened was it landed on heads 28 times, and it landed on tails 22 times. So these things together are called the outcomes. So the outcome of my experiment was flipping 28 heads and 22 tails. All right. Now, if I'm curious about, just the heads, I'm really wondering if, when the coin lands on a head, then we can call, so my main concern, what I'm looking for, we're going to be calling, I'm looking for these heads. Well, that becomes known as an event. So far we have an experiment. I'm flipping a coin. I have an outcome, what happened in that experiment, listing all the different possibilities. Now, one weird possibility that happened to me, I was doing this experiment in class, and I would flip the coin, let it hit my desk in front of me, and let it bounce around, and then record whether it was head or tails. And one of the coin was an old one, so it has very flat edges. And one time it bounced and landed right on its side. I haven't been able to duplicate that ever. So generally it'll come out heads and tails. All right. And then we have, what am I really interested in this experiment? Well, I'm interested when it comes out as heads. So that would be the event. So my event has 28 heads. My outcome, oops, don't even know how to spell again. My outcome has 28 heads and 22 tails for a total of 50 outcomes. And let's put it all together. So if I'm looking for the probability of flipping a head on a coin, then we're going to say the probability of a head, and I'm just going to abbreviate here, is going to equal the number of the events, in other words, the number of heads that I actually flipped, over the number of outcomes. So it's the number of events over the number of outcomes. So the probability of my event head is going to equal 28, because that's the number of events, out of 50, that's the number of outcomes. And then, we could reduce this fraction or change it into a percent. Both of them are very valid. Or change it into a decimal. They're all equivalent notations. Because it's a nice fraction here, I would probably just reduce it. 2 goes into both of them. So this would be 14 out of 25. So the language here would be 14 out of 25. We could also change that to a percent. That would be 56%. You could double check me on that. 14 divided by 25, and then multiply that by 100. Or we can write it as 0.56. So these are all ways of representing what the probability of flipping a head here is. Now there's one more definition that we have to talk about. This whole thing where we actually flipped it 50 times, recorded heads and tails to come up with this probability, this whole thing is considered an empirical probability. So one type of probability is you actually go out and collect data and then use that data to create your probability. So this is called an empirical probability because I actually took the coin and flipped it 50 times to do this experiment. All right, so far, just to be really clear about these things, a couple definitions. An experiment is choosing a situation and determining outcomes. For instance, maybe you're interested in how many people go through red lights at a stoplight. So that would be our experiment, would be to watch cars as they approach red lights, or yellow lights for that matter. And we would record the results. If they stopped, we would say they stopped. If they went through the red light, we would say they went through the red light, and those would become our outcomes. So outcomes are any possible result of an experiment. All right, now when the events that we're interested in, literally we call them events, of the outcomes, in this case would be the number of people that went through the red light. So those are the looked for outcomes. I'm really interested in the people that go through the red light, not necessarily the people that actually stopped. But I need to know both of them so I can come up with the probability of that event being the number of people that went through the red light divided by the number of people that actually drove near that stoplight. All right, so that's all the definitions up to this point, and you have to be really clear when you're dealing with events and outcomes. So another way of looking at probabilities, instead of physically doing an experiment, if we went back to our coin, on a coin, there is one side that is heads, and there is one side that is tails. So we can look at this as just as single coin, and if we were going to flip it just once, the expectations would be that sure, there's one heads and one tail, and these become our outcomes without even flipping it. So this, without even flipping it, so this becomes a different type of probability, but it has some of the same features. So it has outcomes, one heads, one tails. It has one event, just the heads. And if we counted them, we would say that the probability of flipping a head, the number of events would be 1, and the number of outcomes would be 2, the one head and the one tail. So we can say the probability of the event of flipping heads is 1/2. Now, this probability is called theoretical because we didn't even flip the coin. We just kind of analyzed the pieces that make up this experiment. That if we did flip a coin, it has one head and has one tail. Now, one thing that'll happen if we go back a page, that this experiment that I flipped a coin 50 times on the computer came up 28-22, 56% of the time it landed on heads. What happens if I went back to that experiment and kept flipping larger and larger numbers of heads and tails, what would happen is the probability would get closer and closer to the 1/2 that I found theoretically. And that's called the law of large numbers. So here's the website I went to, and this is the last toss that I did. So what I can do is I can keep tossing them 50 times at a pop. The coin flips inside some program, and it will give you the probability. And notice, now it's down to total of heads is 48%. All right. And if I toss them again, the number of heads is 0.5067, which is about 50.7%. If I toss them again, it dropped down to 0.475. Well, that's a big jump. So as the number goes up, we're going to bounce around 50%. So we can see here after 1,000 tosses, the probabilities ended up being 49% for the tosses of heads. So I guess if we went further, and I don't want to spend too much time on that, the theoretical probability would be approached. So again, that's called the law of large numbers. Okay, so there are other, classical experiments that we can look into. One of them is dealing with a die, and die is singular for dice. So when we talk about a die, we're talking about a single dice, which isn't really English correct, but oh well. So if you don't know what a dice is, a die is, it is a cube, and a cube has 6 sides. So when you roll a die, you're only going to have upward facing side of one of the 6 sides. All right, so the outcomes for rolling a die is the set of numbers 1, 2, 3, 4, 5, 6 on a standard one. Well, we're not talking the strange ones. So that would be the outcome. So we would have for one roll of a die, that we would only have 6 outcomes. It's either going to have an upward facing 1, 2, 3, 4, 5, 6. All right. So if I said, what is the probability of rolling an even number as my question, then we have to deal with outcomes and events. So the number of outcomes we already know. There are 6 of them. So the number of events is what I'm interested in. So instead of writing number of events here, I want to come off to the side and say, well, what are the events? So if we're rolling an even number, then the events are going to be a 2, a 4, and a 6. We cannot use an 8. 8 is not on one of the die. So be careful with my questions. I ask some strange things like, what's the probability of rolling an 8 on a die? And the probability there should be, 0. So the number of events is going to equal 3. There's a 2, a 4, and a 6. There's 3 of them. So the probability of rolling an even number on a single die is going to equal the number of events divided by the number of outcomes, which turns out to be the same as the probability of rolling or flipping a coin and getting a head. Now be careful. What we have just done is theoretical, because I never rolled this die. I just looked at the possible outcomes and the events that I was interested in. That's it. So if I was going to do an experiment empirically, I would actually have to physically do this several times, recording what number showed up on the top, counted it all out, and recorded the number of events over the number of outcomes. And we would expect, if we rolled it enough times, that the answer would be about 1/2. Okay. So what about, for instance, we want to find the probability of rolling a number that is at least a 4. Now we got to be really careful with the language here. At least a 4, what does that mean? So if you're at least a 4, that means you are a 4 as your smallest value. So our events here are going to be a 4, a 5, and a 6. So again, when we come up to a probability of this event, Now when things get a little weird, you can write E for event, and it represents rolling a number at least of a 4, is going to equal the number of events, and there are 3 of them. So this would be, again, 3 out of 6, 1/2. Conversely, we can find the probability of rolling one of these die and rolling at most a 4. So when we start talking about at most a 4, we're saying that 4 is the largest number. So when we talk about our events here, we are talking about a 4 is the largest number, and that means we need to go smaller. So we're talking about 4, 3, 2, and 1. So this probability of this event is going to be the number of events, which are 4 of them, out of the total number of outcomes of rolling a die, 6. So this probability would be 2/3. So let's make this outcomes a little bit larger for, a die is just 6 outcomes. It gets kind of boring. There's not much we can talk about. But now, normally, when you're playing a board game, you would roll 2 die, also known as dice, so that you could come up with larger numbers. So our sum of the dice now has a maximum total of 12 and a minimum total of 2. So that's what we're going to be looking at here is if we're rolling 2 dice, now I got to get my language right again, then we're looking for the sum of the 2 dice, generally. But we have to kind of keep the idea separate. We're rolling 2 dice, and therefore we need to be able to record the number that lands on one of them and the number that lands on the other. And it's really hard because they get mixed up. So what we're going to do is we're going to keep one of them like a blue die and then a red die. And when we roll them, we can record the number that falls on the blue die and the number that falls on the red die. So for the blue die and the red, I'm going to just create a column for them. And if the blue die lands on a 1, the red one could also land on a 1. The blue die could land on a 1, and the red die could land on a 2. The blue one, a 1, 3. And that would be if we held the blue die to 1 number and the red die circulated through all its possible values, 1 through 6. So we can do this again and again for the blue and the red, and I'm going to shrink the table down a little bit. Let's go with a different color. Color code these. So blue, red, and then we hold the blue to 2. So I didn't write this fairly organized. It's really big in the beginning and it shrinks as it goes off to the side. But this is all the possibilities. The blue one held at 1, red cycling through all its numbers, blue at 2, red cycling through all its numbers, and so forth and so on. So if I sat here and counted them all up, it's pretty simple to do a little simple math here. There are 6 going down and there are 6 going to the right. So the number of possibilities is 36. So the number of outcomes for 2 dice is 36. So that's just something you want to keep in the back of your mind when you're dealing with rolling 2 dice, that the number of outcomes is always going to be 36. Alright, so let's say we want to find the probability of rolling the sum of 5 when rolling 2 dice. Maybe Park Place is 5 spaces away on a Monopoly board and you want to land on it, and you're curious what your chances are. Alright, so when we're doing probabilities, you always have to keep in mind that the probability of an event is always equal to the number of events divided by the number of outcomes. Now we know the number of outcomes of 2 dice, that's 36, we just discussed that. So my interest is in the event itself. So in the event itself, a sum of 5, if you're rolling 2 dice, you just have to come up with 2 numbers that can roll on a die that add up to 5. So one of them could be a 1 and the other one a 4. One of them could be a 2 and the other one a 3. So those are the numbers that are going to add up to 5. There are no others. And we can go back to our table here and look for a 1 and a 4 and a 2 and a 3. So a 1 and a 4 happens here. That adds up to 5. But that also shows up over here. That adds up to 5. So when we come up with a 1 and a 4, we also have to take into account a 4 and a 1. All right, the same thing's going to happen with a 2 and a 3. There's a 2 and a 3. But here's also a 3 and a 2. So in this table, you can see that it's on a diagonal, that I have to account for all these possibilities. So generally, let me undo all this. When I come up with these numbers, 1, 4, and 2, 3, I also flip them around, so 4, 1, and 3, 2. So this is 4 outcomes, or 4 events, the ones I'm interested in. So then, my probability of rolling a 5, well, I should really be a little bit more clear here, sum of 5 is going to be the number of events, which is 4, the number of outcomes, which is 36, and if we reduce this, this is 1/9. All right, so there's a difference on dice when we're dealing with sums that are odd and dealing with sums that are even. So again, the number of outcomes is going to be 36, but the number of events is going to be a little strange for 8. So first I want to come up with the numbers that add up to 8 that have to be on a die. So you can't say 1 and 7 because 7 is not on a die. The first one I can come up with, whoops, wrong way, is a 2 and a 6. That definitely adds up to 8. A 3 and a 5, that adds up to 8. And a 4 and a 4. So those are the 3 pairs of numbers that I know that can add up to 8. So let's go back to my table. A 2 and a 6 happens here, but then there is this 6 and a 2 way over here. So those two numbers add up to 8. 3 and a 5, 3 and a 5, or in this case 5 and a 3. And then here's our 4 and 4. Now notice when you roll a red, this should be B. When you roll a blue 4 and a red 4 and you flip it, it's still a blue 4 and a red 4. Ugh, I can't even say 4. So this one is one that does not repeat in our table, so there are only 5 outcomes. Sorry, 5 events that we're interested in. So the only numbers you can reverse are ones that are different. So 6 and 2 and 5 and 3. 4 and 4 is the same if we flip it, so we're not going to count it twice. So this one has 5 events. And therefore, when we do the probability of the sum of 8, we're going to have 5 events out of 36. And that one does not reduce, so there's my probability. The next type of probability I'd like to talk about is cards. And we're talking about a standard deck of cards, not Pinocchio. What's it called? Oh my gosh, I can't think of the name. Pinochle. So the next topic we want to talk about is cards. And we're talking about a standard deck of cards, not Pinochle cards, which have basically all face cards in it. So when we talk about cards, it breaks down into a few things. There are 52 cards. And I love asking this in class because then I'll say, well, how many states are in the United States? And people will say 52. And they're not. There are only 50 states. Hawaii was the 50th one. But there are 52 cards. And the cards are broken down into, first off, groups of 4. And that group of 4 is the hearts. I love drawing these things. The diamonds, the clubs, and the spades. Here. There we go. And if it's broken into 4 pieces, 52 divided by 4 is equal to 13. So there are 13 hearts, 13 diamonds, 13 clubs, and 13 spades. All right, we can break this down a little bit further. There are 2 suits that are red and 2 suits that are black. Okay, so the red suits, there are therefore 26 of them, and the black suits, there are also 26 of them. So there are 52 cards, there are 26 red, 26 black, and they are broken up into hearts, diamonds, clubs, and spades, where hearts and diamonds are red, clubs and spades are black. Okay. Now, within a suit, so this is called a suit. Hearts, diamonds, clubs, and spades are called suits. Within a suit, there are cards that are 2 through 10, so 2, 3, all the way up to 10. And then there's a jack, a queen, a king, and finally the ace. Now, depending on the game you're playing, ace can represent 1 or it's the highest card. Or trump for that matter. All right, so the 13 cards inside of the hearts are the 2 of hearts, the 3 of hearts, all the way up to the 10 of hearts, jack of hearts, queen of hearts, king of hearts, ace of hearts. And the same thing for the diamonds, the same thing for the clubs, and the same thing for the spades. So these are the breakdowns of the suit. Now within the suit, there are 3 special cards, these ones, the jack, queen, and king, and they are called the face cards because literally they have faces on them. The ace does not have a face. I love saying that, it rhymes. All right, so we have numbered cards 2 through 10, we have face cards, jack, queen, king, and the ace is kind of its own little thing. All right. So now we can ask probability questions based on cards, and you can see all the possible weirdnesses that are involved with just a standard deck of cards. So, what is the probability of selecting a random card from a deck and that card actually being a heart? So we're talking about like either shuffling a deck of cards, screwing them up on a floor, and just randomly choosing one card out of the mess. Kind of like that magic trick. Pick a card, any card. So our outcomes for this problem are going to be, well, the deck of cards. So the outcomes is the deck of cards, and the deck of cards has 52 cards in it. So it's going to be one of these 52 cards that we're going to select. Now, the event that we're looking for is a heart. And I think where most people get really confused about probabilities is we're picking one card out of 52, and they think the probability of selecting a heart is going to be 1 out of 52. But you also have to remember that events are all the possible things that we're looking for. So since we're looking for hearts, there are 13 hearts in a deck of cards. So it could be the 2 of hearts, the 3 of hearts, the 4 of hearts, all the way up through jack, king, queen, and ace. So we have 13 hearts to choose from out of 52. So when we talk about the probability of selecting a heart out of a deck of cards, the number of events is going to be 13, the number of cards is 52, and that reduces down to 1 out of 4. So I want to use cards to introduce another type of probability. So for instance, what is the probability of selecting a 10 or a face card from a deck of cards? So the word I want to introduce here is this word or. Now, when we're talking about this word or in this situation, we're still picking one card out of a deck of cards. But we're interested in whether the card is a 10 or if it's a face card. So when we do this, we pretty much have an idea that a 10 and a face card are two distinct possibilities. So when we talk about these two distinct possibilities, we call them mutually exclusive. And basically what that means is a 10 cannot be a face card, and a face card cannot be a 10, so there's no overlap. So these are mutually exclusive events. Now for mutually exclusive events and the word or, we're going to have the probability of this event is going to equal the probability of the event having a 10 plus the probability that the card was a face card. So the idea of or turns into plus. Now this is only true, well, I should be a little bit more cautious. Mutually exclusive is only addition between two probabilities. When it becomes not mutually exclusive, we're going to have to deal with it a different way. So we can substitute a few things in here. How many 10s are in a deck of cards? Well, there's 4 of them. 10 of hearts, 10 of diamonds, 10 of clubs, 10 of spades. So the number of events is 4. The number of outcomes is 52. There are 52 cards in a deck. Plus, then we have to ask how many face cards are there? Well, face cards are Jack, Queen, and King in 4 suits, so that becomes 12 face cards out of 52. So this probability is going to become 16 out of 52, which is equal to 4 out of 13. So the probability of selecting a 10 or a face card is going to be 4 out of 13. Alright, let's change it up a little bit. So here I have, what is the probability of selecting a red card or a king out of a deck? So again, we're dealing with two possibilities, a red card and a king, and the key word that's connecting them is or. So addition is part of it, but here we have to be a little bit careful. Are they mutually exclusive? So is there a red card that can also be a king? Well, yeah, there's the King of Hearts and the King of Diamonds. And then if we go the other direction, is there a king that can be red and it's those same 2 cards? So if we added them together, the problem becomes this. There are 26 red cards and there are 4 kings. But in this 26 is the King of Hearts and the King of Diamonds. And over here in this number 4 is also the King of Hearts and the King of Diamonds. So if we added these 2 numbers together, we're adding over here the King of Hearts and the King of Diamonds, but then over here I don't need to add them. They become overlapped counted. So we have to be really careful with this overlap. So this would be not mutually exclusive. And the formula for not mutually exclusive has a little bit of subtraction because of this overlap of the King of Hearts and the King of Diamonds. So the formula kind of looks like this. The probability of A or B, where A is the red card and the B is the king event, is going to equal the probability of the first one plus the probability of the second one. And then we have to get rid of the overlap. The first one already has the King of Hearts and the King of Diamonds. The second one also has it, but we want to get rid of it. So the way we're going to write that is we're going to subtract the probability of A and B. We can also write this as A intersect B, their overlap. The number in their overlap. So they overlap with 2, King of Hearts, King of Diamonds. So the probability of a card being red is going to be 26 out of 52. You could write 1/2, but it's easier to keep things with a common denominator. So I'm going to leave it as 26 out of 52. Plus the probability of it being a king. There are 4 kings out of 52. And then we're going to subtract the probability of it being a red king. And we know there are 2 of them, the king of hearts and the king of diamonds, out of 52. So if we simplify this, let's see, that would be 26 plus 2, which is 28 out of 52, both divisible by 4, and we'll get 7 out of 13. So the probability of selecting a red card or a king at random out of a deck of cards is going to be 7 out of 13. So one thing you will have to use for OR problems is this formula. And you can use it for all OR problems, even the previous one, where we just added the 4 50-seconds and the 12 50-seconds for the 10 and the face cards. Because if we did do a probability of 10 intersect with face, 10 cards don't have faces, so the probability here would have been 0, and you still would have ended up with 4 over 13. So my suggestion is to always use this formula, and if the probability of A and B or their intersection or their overlap is 0, then it doesn't hurt you to actually write 0. Alright, so here's an example based on a table of values. I've kind of just made this up, a high school 10-year reunion, and it's going to be broken up as male or female, only has a high school degree, a 2-year degree, a bachelor degree, which is a 4-year degree, or a graduate degree, which could be master's or anything higher. So my question here is, what is the probability of selecting someone from this reunion who has either only a high school degree or a 2-year degree? So when we start looking at the table based on this information, this is out of the entire group. That's one thing you have to figure out, is what is the total outcomes. And the total outcomes is this entire group of 157 people. The other thing you have to focus on is, what are we really looking for? What are the events? Well, one of the events is a high school degree. So these are the high school degree people. And then the other one is a 2-year degree people. Now we're talking about these numbers, and we just have to be able to interpret them a little bit nicely. So let's write it out. The probability of this event that we're looking at is going to equal the probability they have a high school degree or a 2-year degree. And then the rest of the formula could be minus the probability of both, the intersection of these guys. Or and, either way you want to look at it. So the first thing I want to deal with is the intersection. Notice these 2 orange lines don't even meet. So we're treating this as in, if you only have a high school degree, you do not have a 2-year degree. And if you have a 2-year degree, you're not going to also be in that group of only high school degrees. So this probability here is going to be 0. So these events are not mutually exclusive. Or I'm sorry, are mutually exclusive. All right, then the rest of it is pretty simplistic. So the probability of the event is equal to the total number of high school graduates only are 60. So that is the number of events. The number of outcomes is the entire group, which is 157. Plus, the probability of 2-year is 46 out of the 157. So the probability of this event, high school or 2-year degree, is going to be 106 divided by 157, which I don't think reduces. So in this case, we're going to change it into a percent. 106 divided by 157. So that's about, oh, don't forget, times by 100, because we're changing it to a percent. 67 point. So this is about 67.5% chance of either selecting a high school degree person or a 2-year degree person. All right, that was pretty easy. All right, so again, back to the same table, but a different probability. So here, I want to find the probability of selecting at random a woman or someone with a graduate degree when we, just reach into the room, grab somebody. So again, we're talking about the entire room, so we're still talking about the 157. But when we start talking about women, then women are all the females. So we're talking about this entire row as our females. And the someone with a graduate degree is going to be this column. And you'll notice right off the bat that these two things are intersecting with each other, specifically at that 7. So we can say without a doubt that this is not a mutually exclusive situation. So we're going to do our formula specifically with the subtraction in it. So this becomes the probability of our event that we're looking at is going to be the probability of selecting a woman or a female, plus, that's what the or turns into, someone with a graduate degree, so the probability of a graduate degree, I'll just make that G, minus the probability of the intersection of the women and the graduate degree. And I like the idea of intersection in this situation because you can actually see that these two lines are intersecting at that 7. All right, so let's substitute in what we know, the probability of women. Now we're talking about all the women, so sure, there's a 27 and a 31 and a 19 and a 7, but for the probability of all women, that's going to be 84 out of the entire group, which is 157. And then when we get to the graduate degrees, we're talking about the total number of graduate degrees, and that's 12 out of 157, minus their intersection, their overlap. So there are 7 of them in the overlap out of 157. Okay, so we just need to calculate 84 and 12, that's 96. Minus 7 would bring me down to 89 out of 157. And again, it's an ugly fraction, not really fancy, and it doesn't reduce like 89 divided by 157. And oops, we forgot again. We're changing it to a percent, so times 100. So 56.7. So this would be 56.7% of the time we would be able to select a woman or someone with a graduate degree. So I wanted to introduce the idea of what's called a conditional probability. So if I want to find the probability that someone has a bachelor degree if the person picked was a man. So basically what this is doing is taking the entire room and separating it into men and women and only focusing on the men. So when I go looking for my outcomes, it has to come from just the men. So basically we're ignoring all the females and we're only picking on the males. Now this can happen if you randomly pick someone from the room and they turned out to be male, then you have a secondary question of, do they have a bachelor's degree? So this is considered a conditional probability. There's something first, and then you're looking for a probability based on that something. All right, make sure I'm on the right pen. So here we're interested in men with a bachelor's degree. So let me change my color to something bright. So men with a bachelor's degree are here. Oops. Men with bachelor's degrees are here, where this 20 is. So we have a total number of 73, and we have a sub number or a specific event number of 20. So when we say what's the probability, and the way I'm going to denote this is a little strange, of a bachelor's degree, let's call that batch, given that they were a man. So this weird line here is given that. And you don't have to go through this. I just use it for making writing a little bit shorter. So the probability that a man has a bachelor's degree. So that number of events is going to be 20. There are 20 men that have bachelor's degree out of the men, which is 73. So the probability would be 20 out of 73. On a calculator, that's about this 0.273, but we want to change it to a percent, so times it by 100. And it's 27.4. So this would be approximately 27.4% of the time we will be able to find a bachelor's degree person if they were already a man. And that's what's considered conditional probability. It allows you to look at a subgroup and then find probabilities about that subgroup.